Welcome to StarTalk. I'm your host, Neil deGrasse Tyson, your personal astrophysicist. And today, we've assembled our crack team of science all-stars who will help bring the Star Trek universe down to Earth. We're all here because we know that it's the 50th anniversary of the original series on television, and I'm old enough to have seen that show in its first run, just so you know. And I remember... I said, wow, this is the future. And wow, that's cool. It's got like all different people on the deck, different colors, different accents. I said, that was kind of cool. And I was digging the warp drives, the phasers, the photon torpedoes. This is language from astrophysics, a field that I knew very early I'd be interested in. And I have to confess, I confess this every time I have the opportunity to do so, that while I found all the rest of that high-tech weaponry and discs that go in boxes and data come out and hot food coming out of a box instantly. It was like, yeah, I got that. We got that. And then there they are walking up to doors, and the doors just open instantly. And it was like, no, that'll never happen. We will never live in a world where doors know you're walking up to them. Oh, come on, please. So don't ever take advice from me about what the future will bring. That's just a warning. So tonight, who's going to bring you through tonight is my friend and colleague, astrophysicist Charles Liu, who is our StarTalk resident Star Trek geek-in-chief. This guy knows more about Star Trek than anybody else, almost anybody else I know. And so he's going to take the reins of this session, and I just want you all to enjoy it, sit back, and gain all the cosmic insights, wisdom, and understanding that we can glean on this 50th anniversary of Star Trek. I'm Neil deGrasse Tyson, as always, bidding you to keep looking up.
So hello, everybody. I am Charles Liu. I am an astrophysics professor at the City University of New York's College of Staten Island, and this is StarTalk All-Stars Live. This is our first live All-Stars show, and we're really excited to do it here. I cannot think of a better place to do it than here at the Star Trek Mission New York on the 50th anniversary of the original series of Star Trek. Thank you all for being here. We can't wait to hear your questions and your comments, but right now, let me bring on our wonderful panel. Joining me tonight, first, as my comedic co-host, Mr. Chuck Nice. Chuck.
How are you, buddy?
I am well, thank you.
And
Chuck,
thank you all for coming. It's a pleasure to have you all here, and we certainly appreciate Neil beaming in from his Catskills hideaway.
Catskills?
Did you see all those trees in the background? I don't know where he was, man.
Yeah, there's only the Catskills could there be that many trees.
Absolutely.
Well, Chuck, you are a regular on StarTalk. We've done many episodes together, right? And now we can add all-stars to that list.
Absolutely, and it's very
A lot of fun, right?
Yeah.
Okay, and you know, you may not realize just how much Trek this gentleman has flowing in his...
Oh, we don't need to go into that.
Yes, we do.
No.
Yes, we do.
Yeah. I'm a huge Trekker. I've been a fan since as long as I can remember. And I feel very good that I'm in a place where I really don't have to hide it. You know? That's very cool.
Yeah. We have two wonderful science guests today. The first one, a friend of mine whom I've known for many years, my first time sharing a microphone with her from Columbia University. Please welcome Summer Ash. Summer, I know, isn't this great? In addition to being on StarTalk's new All-Stars, right, and being a host, a StarTalk All-Star host, you're also an astrophysicist, a director of outreach for the Department of Astronomy at Columbia. You're a freelance journalist, an in-house astrophysicist for various cool television type things, a blogger, a writer, a Twitterer, and you totally understand what it means when we fuse science with fiction and put it on television.
I hope so. I like that area.
Yeah, if it's not you, I can't imagine who else would do it. I'm so glad that you're here. Thank you.
Thank you, Charles.
And all the way from Canada, William Shatner's home country, may we add? There is someone that I just met today. I'm very, very, very happy to introduce you all to the person who wrote this book, Star Trek, The Official Guide to Our Universe, Andrew Fazekas. Andrew, thank you so much for coming in. The audience may or may not know already that he is the night sky guy. You are a TV broadcaster, Andrew, a syndicated radio columnist. You write the weekly Starstruck column for Nat Geo News. And since William Shatner wrote the foreword to this book, I think it is only fair that you spend a moment describing what is now the official guide to our universe from the Star Trek perspective. Let us know what you were trying to tell us, and then we'll get right into the science from that book and others. Go.
Well, yeah, I mean, this is a labor of love for me. I mean, I'm in heaven with this, because this has been a book I've been working on for, I guess, about 10 years. 10 years I've been working on this thing. 2 years of, hard labor watching Star Trek episodes.
Oh, hard labor, yeah.
And movies, scene by scene. And what I've done here is cherry-picked episodes and movie scenes that really reflect, I think, the science of the real science so well, particularly astronomical science. My shtick is really showing people the night sky. That's what I've been doing for, about 30 years now. And since I was a little kid, I've been taking out a telescope and trying to get people excited about the night sky, grab them and say, come on, look, that's the rings of Saturn, man.
That would do it. What you just did there made me want to grab a telescope and get out there.
You see, that's what I'm talking about.
Yeah.
That's what it is. So that's really what I love about this. And this book sort of, I guess what I like to call it is a Vulcan mind meld of two of my passions, right? This stargazing and Star Trek coming together in one volume here.
Your thoughts to my thoughts, Andrew.
That's your mind to his mind.
Where is
Feeling
Vulcan in the sky? Where are these things? What is the answer to this question?
You guys are the astrophysicists.
The answer very basically is they're all in our Milky Way galaxy.
Exactly.
Right? You've heard of the quadrants. We live in which quadrant? Alpha. Right? Summer, what is a quadrant in a galaxy? What is the quadrants of our galaxy? And why do we only go in our galaxy? Why don't we go beyond our galaxy?
Because it's huge compared to us.
Is it huge or is it huge?
It depends on if Donald Trump is
say
talking about it. If Trump says it, then it's huge.
Yes, just tell us, what is the size of our galaxy, and how come even with warp, being able to go up to 9.4 when we're trying to chase down the Borg in the Best of Both Worlds Part 2,
Yeah. Why
can't we exit our galaxy?
Because we can't even exit our solar system yet. The galaxy is so big, it's at least 100,000 light years across. We're about 2/3 of the way from the sun, so each half of it is about 50,000 light years. And the farthest that we've sent something right now is one of the Voyager probes, and that is pretty much still around 23 hours away?
23 light hours away.
23 light hours.
Barely a light day.
Wow.
So 50,000 years, not happening. And, we could go up or down, but that's at least, that's on the scale of hundreds of light years still. So anytime, first of all, this is just a fun fact, point of information. Anytime somebody shows you a picture of the Milky Way, it's not the Milky Way. It's a very nice artistic impression of the Milky Way, or it's an example of a spiral galaxy, and it's a picture of another spiral galaxy that we can see from our galaxy. Because we just can't even send something out to take a picture like that.
Yeah, you got to remember that we are in the galaxy, right? Our viewpoint here from Earth is embedded within one of the arms, the humdrum suburbs of the galaxy, right? Because it's sort of like a pinwheel shape, right? So we're on one of the arms that are spreading out from the central bulge of the galaxy, and we're embedded there inside this arm. And so our viewpoint really is only of a partial of the galaxy. Have we actually seen the entire, have we been able to map the entire galaxy?
We haven't mapped every single star, but there are projects that are doing that. So there's Gaia. Gaia is a project that is trying to map hundreds of thousands of stars in our galaxy. And we can take pictures. So actually, there's a one picture exception. And it's if you see a picture of the Milky Way that looks like a strip, that's basically a panoramic that somebody has taken from Earth. And it looks like a dusty plain. With stars, and you can't see through the middle because there's actually, for as empty as space is, like the vacuum of space, there's still a lot of stuff in it. And most of it is gas and dust. And it gets in the way and it blocks starlight from us when we're trying to look with optical wavelengths like our eyes. But the Milky Way looks gorgeous from inside. And I have to say, I think we're in the prettiest suburb I've ever been in.
So really, we are like little tiny fish in a vast ocean trying to map the ocean. Nemo's finding Dory. We're finding Vulcan, right? We're looking for Cardassia. We're looking for Bajor, all these wonderful places that supposedly exist. And let me ask you the following. If we find them, how will we know that they are habitable? What is the classification? Andrew, how do we know something is a world where actually there's something? Never mind the sort of fictional way of saying, oh, anything can live anywhere, right? Which is true. But non-fictionally, what do we need to look for to make sure that life actually can live somewhere on a planet?
Well, right now, one of the big criteria out there that scientists use is looking at this habitable zone around a star, right? So this is what we affectionately call the Goldilocks zone, right? It's not too hot, not too cold, and on this surface of a planet, that is meaning that how far away it is from its parent star. So in terms of liquid water being able to exist on the surface. So if the planet would be too far away from its parent star, then the water would basically freeze out on the planet, right?
So this most recent discovery of Proxima b, right? Those of you who've heard this, Proxima Centauri is probably the closest star to us, a mere 4.25 or so light years away from Earth. Most recent studies, after literally decades of people trying to find a planet around there, seem to suggest that there is a planet there, maybe 1 to 2 times the mass of our planet, orbiting in what we might consider that habitable zone. Is there life there?
At this point, I don't think we can just, it's speculation, right? Okay. And we have to remember, we haven't actually observed the planet. We haven't actually directly imaged this planet. We're detecting the effect that the planet has on its parent star, right? In this case, we're looking at wobbles of the star, because as planets go around their host star, the star actually ends up wobbling because of the gravitational pull and tug of those planets. And what's amazing is that we have such exquisitely sensitive enough instruments today that we can actually take those wobbles, measure them, and understand like how many planets are orbiting around that star, what their masses are. But to take it to the next level is what I think would really take is understand, like, does it have an atmosphere? We know that it's like in Proxima b case, we know that it's 1 to 2 times the mass of the Earth. And with our understanding of planetary physics, we think that it's a rocky terrestrial type planet. So has a rocky surface, someplace solid we could land on, right? But does it have an atmosphere, for instance? We don't know that.
Summer, how do we find out whether there's atmospheres around other planets? Is there a technique or techniques that actually will give us that scientific handle on whether there's gas surrounding a planet?
Yeah, absolutely. But it requires a chance alignment so the method that Andrew's talking about is making use of this wobble. But there's another method that's called the transit method, which is when the planet goes in front of the star and blocks the star's light from us, and we see a dip in that star's light. But that can only happen if, that solar system is in line with our point of view. And in theory, the stars and all of their potential planets are in random directions from us. So not every star is going to have its planets going between us and them. But when they do, The cool thing is that you can actually monitor this star's light, not just the brightness, but actually the content of that starlight, the metallicity, sort of the spectrum of that star, what type of elements it has. And when the planet goes in front of it, if there's an atmosphere, some of that light goes through the planet's atmosphere. And then that changes what the starlight that we record is. And we can subtract one from the other, because when the planet goes around the back of the star, then that signal goes away. So you can figure out what the atmosphere of that planet, what elements it's likely to have.
And Chuck, what would you do if you found a comedy club on Proxima B?
I probably would make sure they have air first.
That's a good point.
Yeah, and then maybe I might take a booking. You know.
The first ever stand-up in space. Andrew, you had something else to add on for a second?
I just think that I'm so excited when I hear that. The idea of being able to have this, chemical fingerprint of the atmosphere, because let's take that to the next step. If we could actually detect the chemistry of an atmosphere, of an exoplanet, we could tell what's there. Imagine if we found things like methane or,
Wait,
oxygen.
methane is like cow farts. Why would I be excited about finding cow farts?
Because cows are on the planet.
Exactly.
Oh, yeah, okay.
Cows. I mean,
All
come
right.
on.
It's also the funniest planet, let's be real.
Farts do make everything funnier, right? Just ask Dr. Nina Strominger.
It's just a rule.
Yeah, okay.
Exactly. Think about it. It's potentially a sign of life, right? Potentially. Or things like chlorophyll. Wouldn't that be interesting? Or how about greenhouse gases or something like that? So there could be some very interesting findings that could indicate very clearly that there would potentially be life on these planets.
Wonderful.
Can I just say that I think it's really funny that the nearest star to us is the one that took us so long to find a planet around? It's kind of like when you're like looking for your glasses and you can't find them and they're on your head.
That is an excellent point. Yeah, no, I think that's a very good point. Sometimes the most difficult things to find are the things that are right nearby, but faint.
Proxima B, you were there all the time.
Wait, isn't there a song from the 1980s like that? The search is over. You were with me all the while.
Very nice.
Hey, American Express card members, you don't want to miss this. Now through December 31st, there's a big reason for you to shop small at local stores in your neighborhood. Learn more and enroll your eligible card today at americanexpress.com/shop small offer. That's americanexpress.com/shop small offer. Terms apply.
Bringing space and science down to Earth. You're listening to StarTalk.
Science fiction. Double feature. Dr. A.
So you all are here. Thank you again for joining us for our StarTalk All-Stars first live show here at Star Trek Missions New York. On the 50th anniversary of this wonderful show, Star Trek and everything has come as a result of it. We're going to zoom out a little bit now and talk a little bit about some of the science about the cosmos that shows up. All right, you've heard now about the planets, about the Earth, now let me ask you about the universe itself. And the first thing I'm going to ask you is warp drive. We have to know about warp drive. Obviously, the only reason you can get from one place to another in any reasonable time before the show gets canceled is warp drive, right? So how can warp drive actually work? Does space-time actually warp? Summer.
It does.
Well, we've cleared that up.
Now we can move on.
Now you can move on with your lives because warp drive works.
Oh, she said space warps, but can we use it to drive? Because I want to mention a Mexican physicist in a little while that came up with something. But please, Summer, first tell us, how does space warp exactly?
Oh, so space warps because, like Charles said, space and time are kind of this thing together. And they're this fabric of the universe, we say. So things with mass, actually, this is what Einstein's theory of gravitation tells us. It basically says that because space and time are one, an object in space-time warps the area around it. And so that's why objects that get within a certain distance of something more massive than them will fall towards it and eventually go into orbit around it. And so this will happen, I mean, you're warping space right now.
Am I?
Yes. Everybody
me?
in here is exerting gravity on everybody else.
I thought I
No
smelled
such thing as personal space. But none of us are big enough to outweigh the other thing that's attracting all of us, which is the earth beneath your feet. So it's warping space, so we're stuck to it.
All right, well, that's nice. I have here, by the way, my original series era communicator, right? Which we will use as a prop to define gravity. Okay, so there is the communicator warping space and time. So why can't we just use warp drive? Why can't we just warp space and time in front of us and before us and just drive on through?
I don't know, do you have enough mass just sitting in your storage area to do that?
So we need mass.
That's my...
Chuck?
I'm fresh out of mass, but thanks.
Man, Andrew, got any mass you can spare?
No, I need everything I can get.
How much mass precisely will we need to warp space and time to such an extent that we actually travel? Okay? Well, let me tell you something that somebody said in about 1994. There was a Mexican physicist named Miguel Alcubierre. Miguel Alcubierre wrote a paper speculating that it might be possible for something in a bubble to move faster than the speed of light through space. Even though you cannot move through space at or faster than the speed of light if you have any mass at all, Alcubierre hypothesized that the mathematical equations of general relativity were flexible enough that if you could create an asymmetric bubble in space-time, one part compressed, one part expanded, it would propel whatever's inside that bubble forward through space at faster than the speed of light, or even slower, faster, doesn't matter, right? So that would be very cool.
Yeah, it would.
Does that make any scientific sense?
It's theoretically possible, but can we actually build a spaceship that would have enough power, generate enough power to do that, bend space-time?
Well,
like that?
apparently all we need is some antimatter and a dilithium crystal, right?
Right. That's all you need.
Isn't that a nice thing to do? But in true physics, how much mass would be necessary? Would a planet-sized object be enough to do that kind of warping of space-time?
Charles, I'm an astronomer, not a physicist. Just kidding.
That was very Bones McCoy of you just then. I'm an astronomer, not a physicist, damn it.
Actually, do you all know the difference between an astronomer and astrophysicist, right? When I am on an airplane and someone sits down next to me and says, "Hey, so what do you do for a living?" If I want to speak with this person, I say, "I'm an astronomer." And if I would rather be quiet and not speak with the person, I say, "I'm an astrophysicist."
Yeah, that works every time.
But I know that you have a specialty in radio astronomy, Summer.
I do.
You understand things that produce radio waves out in the universe.
Yeah, they're the coolest.
They are cool. Can you give us a sense of, say, 2 or 3 such things that we have run into? Or by we, I mean the Enterprise, X, A, B, C, D, E. That's enough.
Okay.
Yeah, we'll stop there.
Well, stars give off radio waves, actually.
Really?
Yeah, I mean, they're just not the brightest in the sky, but
Okay.
like our sun. So any given star is going to show up if you look at it with a radio type of telescope.
Okay.
And also, I just want to clarify, because this can be a source of misconception. Radio, even the radio that most of us don't have anymore, we have wireless, we have Spotify and Pandora, but the radio in your car, the radio, your old boombox, for those of us that know what those are, that radio's light, actually. So your radio is picking up a light signal that's in radio frequencies, and then it's turning it into sound that comes out of the speakers. When we talk about the radio universe, we're not talking about picking up I mean, we can pick up signals that we can turn into sound. But radio astronomy is looking at things with radio telescopes, and you can see the coolest types of light. So you can see supermassive black holes, and they look nothing like an actual galaxy. So you can see a pretty picture of a spiral galaxy, and then you put on your radio glasses, and it just looks like giant jets just spewing out into space and shooting particles and hot plasma out there to like scales 10 times the size of the galaxy.
But can you pick up a classic rock station?
Yes.
How about some classic...
It's extragalactic FM.
How about some classic surfer punk while you are driving an old starship through a whole bunch of drones that are heading toward a really, really oddly gravitational space station? How real was that? How possible is it? For those of you who haven't seen the most recent Star Trek movie yet...
Spoiler.
Too bad. Sorry.
By the way, just because you should have seen it by now, Picard ends up pregnant. Sorry. Sue me.
Right. So that is a very interesting science that was shown in that particular space station, right? Andrew, if you saw that movie, you saw that people were walking up and down, sideways, left and right, and so on. Was that some weird artificial gravity effect, or can that actually happen in real physics?
That's a good question. I'd ask Summer.
Oh, we'll ask the non-physicist
Yeah.
astronomer person, right? Come on, Summer. You're a physicist as much as I am.
So actually, I did not see it.
Oh.
But I
Okay.
do know about
Then
creating
imagine-
artificial gravity.
Yes, imagine a smorgasbord of weird things like going this way, your escalator's going this way like an Escherian painting, and yet your hand is drawing your other hand while your brain is up here, and the environmental system is spewing out this black stuff, okay? Or not.
Were you on anything when you were watching that?
Well, the popcorn
picture
butter was
it.
pretty darn amazing, I have to say. It's true. But yes, tell us about artificial gravity. Is there actually physics to artificial gravity?
I believe there is. So some good examples of it are in 2001, the spinning space station.
So is there a way to make artificial gravity the way you see it portrayed in most sci-fi without the spinning? So the physics of the spinning, of course, that makes sense with the centripetal force, but when you see a ship and it's just traveling and everyone is just not floating, is there a way to feasibly create that environment?
No.
Oh, man.
I am so sorry
Well, we
I
can
asked that
dream.
question.
Well, okay.
I would love to have that.
Well, what about gravitational waves?
That's a whole different ballgame.
Yeah, because we were talking about like warping space-time,
Space-time,
right?
yeah.
And recently, a very, very big deal was made of gravitational waves. Can we not just surf along a gravitational wave and actually like travel where we are? How does that work?
Actually, what I would really like to get are the boots that Channing Tatum had in Jupiter Ascending, because as he described it, they change differential equation slips so you can surf them, which makes total sense, right?
Well, it does to me. Sorry, everybody.
So gravitational waves are, so Charles had this fabric of space-time
Oh,
there.
right. They go too soon.
And gravitational waves are basically when there are two massive things that end up merging. Two black holes in this case. So two black holes, one was, they were roughly both 30 masses. One was a little higher, one was a little lower.
30 times the mass of the sun, yes.
Exactly, sorry. 30 times the mass of our sun. And they were orbiting each other because actually most stars exist in binary systems. Our sun is kind of an exception, but we think 2/3 of the stars in the galaxy are roughly that. I'm not sure if that's changed, but binaries. And a lot of times they can evolve in lockstep or they can evolve one ahead of the other, but you can actually get a case where you have two black holes as the result of a binary at the end of their lives. And they are warping space-time and they're actually losing energy, so they're falling towards each other, and then eventually they speed up, and then merge. And then all of space-time goes rippling out, kind of like somebody threw a massive rock in a pond. And so that ripple went through the Earth. And it was detected by two different observatories. And when I say observatories, in this case, these are not types of light whatsoever. This is space actually stretching. So these observatories, LIGO, it's called Laser Interferometer Gravitational Observatory, are two arms that are 4 kilometers long. And at each end of each arm is a mirror, and in the middle, there's a couple different beam splitters and a laser. And the laser is basically being split down each arm and bounces back off those mirrors. And it's set so that when the light comes back, it looks like everything's perfect, they're exactly the same length. But a gravitational wave passes through, and one of those arms gets a little bit longer. And then the light looks funny, and the scientists can do the math, and they can back that out. This happened, and the length that one of those arms stretched was the width of a proton.
Wow.
So
And we detected that. We're good.
That's a millionth of a billionth of an inch on something that's more than 2 miles long, and it was able to be measured. This is what your tax dollars are paying for, ladies and gentlemen.
Thank God.
Yes.
I know.
All right.
Thank God.
Thank you so much.
And how cool is it that from that tiny, tiny, tiny little length, we're like, oh, that's a black hole this big and a black hole this big, and they're about in that direction, and they totally collided.
It's amazing. Andrew, where is the nearest black hole to us?
Oh my gosh. Well, there's a few. There's a few candidates, and it's very controversial exactly how far away. But one of them is near in the Sagittarius constellation. So you would be right now at this time of the year. It's something that you would be locating in the southern sky late at night, about couple hours after the sun has set. So you'd be looking low from here in New York. It'd be low in the southern horizon. You'd try to get out of the city, of course. You want to see but you'd be able to see from a dark location, maybe where Neil is in the Catskills, maybe perhaps.
If there's not too many
perhaps
trees.
you can see it. And there is one that's about 6,000 light years away. So what's neat is to think that when we're examining these objects, right, everything in space is so far away. We use the measure of light years because that's how when we say something 6,000 light years away, means that light has taken 6,000 years to reach us here on Earth. So we're observing that object as it appeared 6,000 years ago. But of course, in terms of black holes and lifetime of stars, their lives are measured in hundreds of millions to billions of years. So changes are not really that obvious unless we really get very exquisitely sensitive instruments, right?
Yeah. Oh, it's wonderful. So let me just bring up 2 more things from the Star Trek episodes, and then what I'd love to do is for people to ask some questions of us, things that we can answer from you about the science that has shown up in Star Trek a couple of times. And I just want to ask you two about 2 things that were mentioned in Star Trek The Next Generation, which I still don't really know that much about, okay? In the episode of The Next Generation entitled The Loss, the Enterprise is almost sucked into a cosmic string. What is a cosmic string?
A cosmic stream?
String.
Oh, a cosmic string.
String.
Oh, well, yeah.
And then, of course, later on in the series, in the episode Disaster, the Enterprise runs into a quantum filament. And then, as you all know, right, Counselor Troy is first to assume the bridge, and then O'Brien is saying, we ran into a quantum filament. She says, oh, so that's like a cosmic string. And then O'Brien said, no, that's a totally different phenomenon, right? Was I good? That was okay, right? Yeah. So what is a quantum filament? And are they actually different things? Do they actually exist?
I have no idea. But the word quantum to me means really tiny.
Yeah.
So a big ship running into something really tiny doesn't seem like a problem.
Well, my understanding is that they're just possibly remnants of the Big Bang. When the universe was very small, there was an imperfection in the actual expansion of the universe at the moment of inflation or just after the Big Bang, then magnified any imperfections that were tiny and turned them gigantic. But I do not know. So if any of you out there, those of you who are in line waiting to ask questions, you know the difference between a quantum filament and a cosmic string, please inform us all, and let's write a paper together, okay? We'll submit it to the Astrophysical Journal. Thank you so much.
With a microphone, and I can split the atom of a molecule,
Bringing space and science down to Earth. You're listening to StarTalk.
Say you kill your heroes and fly, baby, don't cry. No need to worry, 'cause everybody will die.
Okay, so we are ready here on Star Talk All Stars Live to take questions from the audience here at Star Trek Missions New York, the 50th anniversary. It is a tremendous pleasure to be here. Let's start over here. Yes, please. What is your question?
Yes, I wanted to know if it's true that in the future the transporter technology will become real.
Great question. Andrew, you want to take a crack at that? And then Chuck, I want you to take a crack at that afterwards.
I can tell you I would never want to be in a transporter.
Wow.
Everything that I learned, even if they developed it, I would not go. I'm like McCoy. I just hate those damn things.
I'll be damned if I get in your molecular egg scrambler.
That's right. Spreading my molecules across the cosmos.
The thing
thanks.
about transporters, which I would say, is that you have to get every single subatomic particle in its exact quantum state completely replicated, right? But there is this thing called the Heisenberg uncertainty principle in quantum mechanics, which means that if you take a particle from one location and move it to another, there is a certain amount of you don't know what's going to happen no matter what. So I personally think it'd be a great idea to have a third head. Okay, but I don't know that my hands would want to have become heads if I get transported. So until we can solve the uncertainty question, right? And you've heard like, oh, the Heisenberg compensators are not in flux. We don't know what's going on. And boom, Picard becomes a kid, right? You've seen that kind of thing happen. But that's a very good question. So at this moment, I would say, so the answer is probably not.
No.
No? Okay. Yes, thank you. Yes, your question, please, or comment.
Hi, how you doing?
Very well, thank you.
So my question is, you mentioned earlier about the Voyager probe that was the farthest thing that we've sent out in space so far, and I know that in the motion picture Voyager is, Voyager and it comes back and everything. Right. But my question is about the real one, where how far out can it go and still be able to reach Earth, and we'll be able to be in contact with it and receive signal, and how do we receive the signal in the first place?
Oh, that's a great question. Summer, do you know that?
That is a great question.
Yeah.
Well, it's got a radio transmitter on it. It's actually not... We can't actually send signals to it to tell it to do things anymore because it's running on batteries. It's too far from the sun for any solar power, so it's just going to go until the batteries go. And I believe there was either a malfunction or the batteries went on Voyager 2 already because we're out of touch with that one.
Yeah. Mm-hmm.
I mean, it can go forever until it hits something, which it's so small compared to things, that's very unlikely. And so it's kind of pinging us, and it can ping us enough and tell us the composition of the space around it, I believe, because that's how we had the most recent news about it leaving the sun's magnetosphere, the sun's solar influence, but not the gravitational influence. So there's a hilarious comic. Does anybody know XKCD?
Oh, yeah. How do we not know XKCD?
One of the best ones is how many times has Voyager left the solar system? Because there's so many different ways to define the edge of the solar system, and also Voyager has sort of gone through a bunch of different transitional phases that we've never been sure, like, oh, is this it? Is this it? Is this it? And so now we think that it's confident that it's outside the magnetosphere, but it's still not outside the solar system. It's still going to go, it still hasn't passed the Oort cloud, like that's hundreds of years away.
Andrew, do you know how long the batteries will last? I know that we receive the signals using our deep space network.
Right, and it's radioactive decay, right? That's
it's being powered by radioactive generators?
That's right.
Oh.
Right.
Yeah.
So
I thought they were energizers. I'm sorry.
Energizers, yeah. I think it's coming close to the end. I mean, and there may be another decade.
So they're 40 years out now, so maybe 10 more years. I believe the radiothermoisotopic thermoelectric generators were supposed to last 20 years. And it's already after 40, so...
We got our money's worth.
Yeah.
Apparently, NASA does build them like they used to, right? Thank you very much for your question.
Thank you.
And I just want to add to the Deep Space Network, because if you haven't seen it, you should Google it. And JPL, there's a guy at JPL who made a
Jet Propulsion Labs.
Jet Propulsion Laboratory, who made a visualization that's actually up on the screens in the mission control room at JPL. And it has the Deep Space Network antennas that are on the ground. And it can show you which antenna is talking to which space probe. And it shows you whether it's talking, we're talking to it, or it's talking to us. And if it's sending data or we're sending data, it's kind of the coolest thing ever.
Yeah. And I know that the Voyager signal is now weaker than 1/10 billionth of a watt by the time it gets to the Earth. So it's pretty amazing technology. Yes, go ahead.
We talked a little bit about lasers already.
Yes.
And using lasers for minute tasks, whether it be a laser pointer, whether it be surgery, etc.
Yes.
How about phasers? Is there any scientific ability to take lasers or something to that extent and have them impact and cause damage to something possibly the size of this building, the island of Manhattan, etc.?
Are you an evil genius? You're just looking for ideas?
That's a great question. One thing that I'm pretty sure is going to happen is that phasers will not evolve from lasers. Because lasers are a specific kind of coherent light beam, and you're exactly right. They're micro type things. They're very precise. Whereas phasers clearly are like, the death rays of the olden days, right? But are there energy beams that can be harnessed in that way to cause damage on a physical level? Summer, do you know? Andrew, do you have any ideas?
Military, DARPA, I think, are working on laser-based weapons.
Mm-hmm.
But the lasers that I'm more interested in is the idea of communication, extraterrestrial communication, using laser beams for that. There's searches now, aren't there? I think looking at lasers, powerful lasers, powerful enough to cross the cosmos and be able to communicate. So
wonderful.
Ooh, there's also science about using lasers to either cloak your transit signal or make it so it's clearly artificial and doesn't look like realistic, so you can announce your presence if another planet is watching you transit.
Wonderful. Thank you. We have so many people who have questions. Let's get as many of them as we can into that. It's wonderful. Yes, sir, over here.
Hey, and lasers as propulsion too.
Oh yes, that's true. The pressure of the light can actually push something forward in the no friction environment of space. That's right.
Which actually would cause a problem if part of my next question were actually true. Whenever they go through an asteroid field in Star Trek, in Star Wars, in Cosmos even, they always show the asteroids really, really close together, and that's something that's bothered me for a long time because it's just not true. I was wondering from the panelists what's something from Star Trek or related that has bothered you that's really kind of scientifically inaccurate but makes for better writing.
Oh, great question. Can I just go first?
Yes.
Okay.
Do it.
In the Next Generation episode, Starship Mine, at the beginning of the episode, Captain's log, whatever. The Enterprise is at the space station so that it can have its excess baryons removed. Okay. And baryons are protons and neutrons. So if you're removing the baryons, everything's gone. Everything.
Well, that's why if you get caught in the baryon field, you die.
I know, right? But that was just so funny. I saw that. I was like, yes, I'm removing excess baryons from the ship. And I was like, looked at the person I was watching the show with together at the time, who happened to be an astrophysicist who got his degree from MIT. We stared at each other and we just went, ah! We started laughing. We just died. And my poor wife was like, you guys are morons. That's my favorite story. Thank you. Anybody?
Well, so I have one from the original series. Because I just rewatched it again recently, the episode Nomad, where there is a space probe
yes,
that sort of has been altered in its mission, but they bring it aboard and they are trying to communicate with it. And so Kirk says, if I show you like our star maps, you can see where we're from. And the star map was literally a poorly drawn version of our solar system.
Error! Error!
I'm like,
sterilized!
Yeah, that's not going to tell you anything about where we're located.
Somebody got that, right? Okay. Yeah,
I got it.
You got it? Okay, because it's from that episode.
Yeah, exactly.
Yeah, okay.
And so
sorry,
instead, though, what they could do, speaking of Voyager, is that they could have used the pulsar map, which obviously had not been created at that time. But the pulsar map that's on the Voyager record, that's on the Voyager probes, is there to show where Earth is in relation to the pulsars in our neighborhood of our galaxy, because the pulsars have such precise timing that another civilization should be able to also have observed some of them and then like kind of triangulate eventually.
Yeah. That's why that was put on the plaque, right?
Exactly, yeah.
The golden record?
To say, here we are, come.
So they can come and find us?
Come find us.
Please find us. Take our natural resources.
Great idea. Hey, you alien life form clearly superior to us because you can get to us. Why don't you come on over?
Yes, question.
Good evening.
Hi.
There was an episode of Next Generation that dealt with the idea that using warp drive repeatedly in the same area of space might cause a rupture, which was kind of obviously a comment on environmentalism, but in the Star Trek
context. Yes, indeed.
Obviously, that idea would be so far ahead of us to even think about. But is there any way in which environmentalism in our interaction with space has come up in any of the technologies and space exploration, things that send out there?
Yeah.
I will say that when the Deep Impact mission was going to launch a chunk of metal into a comet, Temple Tuttle, I think it was.
Yep.
That, and then there was somebody that tried to sue NASA, saying that we were messing up the environment, the vibes of the universe by messing up that particular thing. I don't know, did anything come out of that?
No, the person actually ran out of marijuana and gave up on the case.
But there is the idea of forward contamination for planetary missions.
Oh,
that's a big issue, right?
That's a good point.
You know, we get some microbes hitching a ride on one of our spacecrafts and we send it to, say, Mars, right? This is a big thing of sending our little germs there, and then how do we detect life for real on these planets if we're contaminated?
The Cassini spacecraft, when its mission ends, it's not going to go, just let it go, right?
No, they're going to crash.
There will not be pollution.
Yeah,
Instead,
because they don't want to contaminate Europa.
Right.
Sorry, Enceladus.
Enceladus.
But Juno, they're doing the same thing with Juno around Jupiter, that when it's done, they're plowing it into Jupiter to not contaminate Europa.
So the answer is, I guess we are environmentally aware of the solar system and maybe the universe. Thank you.
There's a NASA office called the Office of Planetary Protection.
Hey. All right.
On the ball.
Yes, go ahead.
So with the recent excitement of SETI, I'm curious to hear your theory, being both master of science and fans of science fiction. If first contact was a realistic thing to happen in our lifetime, how would you imagine that would play out? What type of intelligence would we be dealing with? And what would it take on our end to be able to really conceptually establish communication?
Wow. I just want to tell you that on April 5th, 2063, I will be in Montana. Okay. I'm just telling you that. It's going to be a great vacation. We're going to drive out there, enjoy Yellowstone, whatever. And then on April 5th, I'm just going to stand there. And I'm just going to stand there. And I bet you all will stand there with me, right? April 5th, 2063. Yeah, actually, is there a realistic scientific way to deal with first contact?
Well, I think there's a protocol that they've put together for that. And,
Nanu, no?
Yeah, well, that's right, of how we would go about doing that. But it's very controversial, too, because do we want to announce, and you have to remember, if we do get a signal, let's say we're looking at radio signals now, how far away these are. I mean, it's more likely a one-way conversation. I mean, they're going to go hi, and that may take what? If it's 500 light years away, it'll take us to say hi back, and that's another 500. It's like, what kind of conversation can we?
Worst remote delay ever.
That's right. That's right. So
wow,
that's a big issue, right?
Yeah.
In terms of communicating,
So
there's actually a job a guy at SETI has that's called Director of Mission of Message Composition.
Oh.
Yeah.
Are you looking for a job?
He's
Sounds
the one
like
deciding what we're going to say.
That's great. I hope he says nanu nanu. But, thank you. Great question. Yes.
So there was a episode of Voyager, I think it was either the second or third episode, where the Voyager crew finds themselves in this time loop, and they actually see and receive a transmission from themselves about like a couple of hours in the future.
Yes.
And I was wondering, how scientific is that phenomenon? Is that based on a real theory? Is that complete TV?
That's a great question.
Do you know?
Here's what I know about that, and then please add in if you understand. When radio signals get sent out, they get scattered all over the place, right? And if you have an appropriate environmental situation, like a highly ionized cloud of gas or something, it is possible to reflect some of that off of that and come back. All right. There is a time delay that happens as well. For example, around supermassive black holes, if you have a kind of a graphite dust or other kind of dust that has a special orientation to it, and then you have magnetic fields that hold that orientation, they almost act like a side mirror. Sort of like Spider-Man's, vision thing on the side. So the light that goes to you gets to you first, and the light going out sideways bounces off and then comes to you later. Right? That's a time delay thing, and that's also, this light is polarized, and so you can see all kinds of neat things that are unusual. So there is possible to get multiple signals, like from various physical sources of doing that. That particular episode might have had more details than that. Is there anything that you'd like to add to what I just said in terms of getting multiple signals or getting a time delay in what we have in the past? I think we're pretty good. Chuck?
Yeah, I think you covered it. Yeah. I'm going to go with what he said.
Okay. Thank you very much. Yes.
Hi. My question may be simple compared to some of the other ones.
No question is too simple. We love this.
Can you guys explain star dates?
Star dates. Oh, gosh. Star date. Come on, official guide, dude.
Well, for my book too, I was looking at star dates, and I was confounded with how they came up with it. It's all over the place. And the last, I found the most sense in this, in the reboot series. It was very simple. It's the year and dot how should I say, the number of the day of the year.
Based on
so it'd be 2016 dot 224 or something like that for the day of the year itself.
But it's based on the,
Yeah, because the day of the year would have to be based on a revolution around what?
Earth.
Our sun?
Yes,
so it would be...
So
it's the date.
It's based on the
date. That's the answer. It's the date.
But my
Earth date based on...
You just don't say May or June.
But my guess is that all had to be retroactively retconned, right, to make it work, because I have no idea how they work either. I think it's just stuff, people saying stuff, which is really cool. So we are basically out of time, but I want to get to all your questions. So let's get to all the questions that are in line, and then we will call it a show. Does that sound like fun? Okay, thank you all. Really, we very much appreciate it. If you have to go, you really got to catch the last 45 minutes of Star Trek II, The Wrath of Khan 4K. I completely understand, but we've got some great questions coming up, and we're going to finish this up coming up here. Yes, please, go ahead.
Pardon me for the simple question. I'm
not at all.
Specifically impaired.
No, you're not. No. Remember, I'm a professor. I have to tell you this. Nobody is scientifically impaired. Science is beautiful and it's wonderful, and you are all good at it. It's all a matter of whether you've got the training to write it down. It's like, I could be Swahili impaired, right? Because I don't speak it. But that's not because I can't do it. It's just because I haven't done it yet. That's where you are now in life. Always remember that, okay? Always remember that. Thank you. Please ask your question.
Thank you. I've always been curious, in any way, shape, or form, can the shuttles going up or rockets going up mess with the weather?
That's a great question. Andrew, do you have any insight on that?
Nope.
Okay.
Nope.
Summer?
So I am losing my mind.
Summer?
So I don't think that there is a causal effect. There could be a correlation, but correlation does not equal causation. probably weird weather you're more prone to notice, and a shuttle is something you're also more prone to notice. So it just might be sort of observational bias. But there are people that do study sort of rocket plumes and the exhaust of rockets and what they do to the atmosphere. But it's a very local phenomenon, and they dissipate within a certain amount of time, and probably nothing on the scale that could really affect strong weather patterns.
Okay. Cool. Yeah, no problem.
It's my educated guess.
That's very likely to be true. And because clouds form by nucleating around things, you can imagine that an exhaust plume could cause clouds to nucleate, right? So locally, as Summer says, it may actually have a good effect. So that's a very good question. See, not at all bad question.
Now go ahead and write your first science book.
Here, let me mention a couple of science books while we're at it. We have to show this is available downstairs in the exhibit hall, so please remember that. This is Andrew's book, Star Trek: The Official Guide to Our Universe. Okay, and this is StarTalk, the book, with Neil deGrasse Tyson. And feel free to enjoy these. These and many of the questions that we've had are in these books, and we're here all day, right? Yeah, okay. So let's get to the rest of the questions. Please, your question.
So subspace is largely a fictional concept.
Yes.
Sci-fi. I saw a very interesting hypothesis that discrete subspace layers are represented by the warp function number, so that you reach a threshold and then continue to the next layer, and the energy goes up.
Like the 7 layers of hell.
Dante was on to
something. We've already kind of covered going through wormholes and warp drive. So I was thinking, how would they justify that within the idea of subspace communication? Because in theory, it should take a long time for the signal to go and then to get a reply. Picard should be sitting there waiting for a reply to happen.
Yeah.
Yet they kind of use the narrative device to speed up the production of having instantaneous communication. So how would subspace communication work in a more practical standpoint?
And you want to take a crack at that, Summer?
idea.
Okay. Subspace, if it exists and is basically our space-time or some version of our space-time, right? Because string theory does allow for the existence of other space-times in parallel with ours. If you are going through these boundaries that get us from one space-time to another through, say, membranes or some other kind of string or structure supersymmetry or something like that, each membrane has its own threshold. But those thresholds, we have no idea if there's actually any physics involved with them. Do they have actually an entropic barrier? Are they just so separated that they never come across? Or are they instantaneous under the right circumstances? So in that kind of context, I can see that there could be an effect, but there doesn't have to be, right? And then the issue of total internal reflection or partial reflection between layers, if that happens. But this is something that I really don't have a good answer to. But that's a good question, though. Yeah, because we're thinking about the string theory side.
It played a big role in Star Trek. It allows us to see a wonderful, episode play out and allows those stories to move forward. I mean, that's the same idea with transporter system, the warp drive. It allows us to have these wonderful stories play out.
Very true. And that's why we're all here, right? Yes, question over here. I love your hat, by the way.
Hey.
I don't know if there's a Pikachu Trek coming up, but I sure hope it is soon.
I really don't know. Out of all the ways that they've traveled in Star Trek, what's your favorite way? Like, what way would you choose and why?
Great. Chuck, what way would you like to travel?
Unfortunately, there's no buses in space. No, I mean, to be honest, I think to be able to travel at warp speed would be just unbelievable. To be in that position. I mean, just to be able, because the bridge has a visual. So can you imagine the visual of traveling faster than the speed of light and what that would look like as you're sitting on the bridge of a ship watching that go by you? I don't smoke marijuana, but I'm puffing away while that's happening just to trip out on that, okay? Because that's got to be very, very trippy.
Yeah.
If you're faster than the speed of light, though, all the light's behind you.
Well, you know what? Now you just ruined my whole thing.
Sorry.
Oh.
Andrew, do you have a favorite travel?
No, I agree. I was going to say warp, because for me as a stargazer, you know, everything is remote, right? Everything up in the night sky are these little points of light. And, you know, I take my telescope, and no matter how big of a telescope I get, I'm still remote. And then to have this capability to go to these places and have ringside seats. You know, this is what I love about Star Trek since I've been a little kid, is Star Trek allows me as a space geek to get these ringside seats that are otherwise impossible. And with today's technology, right, the film technology, we have these hyper-realistic visions of space. And just like with the new movie, I mean, obviously, you know, there's some elements that go, well, that's not realistic or something, but it allows me, like the portraits of Nebula, for instance, you know, even going back to like Wrath of Khan and the Mutara Nebula, that has stayed with me
That
since
is
I was
my
a little
favorite nebula.
It is.
Mutara Nebula.
And by the way, that's kind of modeled on the Orion, the Great Orion Nebula, which you can see every winter. That's on my front cover. By the way, I told them I got to have that because it's beautiful, and it really does look beautiful. I mean, look at the Hubble Space Telescope. We are now capable of really showcasing nebulas, for instance, these gas clouds in space so well, and they play an integral role in many Star Trek episodes. And so having warp speed to get there and to just hang out and see these objects would be awesome.
Wonderful. Summer?
Oh, I just like the part of the hanging out. Like, I would just sit next to a window of any ship and just look out. Yeah. Because that's like my favorite thing to do if I can go to a dark sky, is just sort of sit underneath it and just look at it.
My favorite way of travel would be to go through the wormhole right next to Deep Space Nine. And to go to the Gamma Quadrant and watch all those swirly things go around. That would be my favorite way to travel.
And think of all the things you could explore, things that we would not be able to see otherwise without having that transport system.
Absolutely. Yes, go ahead. Oh, wait, over here. Yes, please go ahead.
So the Goldilocks zone, is that unnecessarily limiting our choices of candidates for possible life? Given our observations with sea vents and the moons out in Jupiter and Saturn, and how much gravitational energy that's possibly biologically, usable, are we limited by just focusing on sun energy on the surface and the atmosphere?
Andrew, Brand, you have an answer to that, and then Summer can follow up.
So in terms of you mean searching for life?
Yeah, where the life could be, because we have the tubes down in the ocean, they get no sun energy to speak of.
Right.
And that could be happening out on the moon, at Enceladus or Enceladus, the moon of Saturn.
Exactly. And that's, and that's something.
Are we limiting our choices?
The ability to see exomoons, not exoplanets, the moons of exoplanets is something that I think we're just starting to, that's really a big endeavor. There's a race around the world amongst astronomers to really be able to see it. We theoretically think, just like we thought exoplanets were around, the time when Star Trek started, it was a theory, but now, it's reality. But the moons, around, say, Jupiter or Saturn.
But with the high density of binary stars, you have all that gravity as energy. Is that possibly a better way to focus?
Summer?
Yeah, I think what Andrew's saying is that we sort of have to start with what we can do. Yeah. And so basically what we can do now is see planets around stars and figure out how far away they are, and then start figuring out if they have an atmosphere and if they're in the habitable zone. But you're completely right that as far as the most likely place in our solar system for finding signs of life right now, it's probably Europa. And then maybe also Enceladus. And so that shows us that once we are able to learn more about these other solar systems, that then we can start thinking about exomoons and also just extreme environments in general, because I totally agree.
Baby steps.
Yeah.
Thank you.
There's actually an astronomer at Columbia right now, David Kipping, who came from Harvard, and he's originally from England, and he does exomoons. So he's going for it.
Yes, go ahead.
I have a simple question. What is the galactic barrier?
The galactic barrier, which theoretically happened in a couple of episodes, and then also at in the fifth movie, The Final Frontier, the one we owe it all. Well, never mind. that galactic barrier was supposedly something that we could not penetrate unless we had some sort of tremendous, magical, energetic push through that barrier. Is there anything physical to that barrier? Did that actually come from something that might be physically true? Andrew's shaking his head.
The only thing that I've come across is the fact that there's a supermassive black hole at the center of our galaxy, just like it exists in probably most galaxies that we see. These monster black holes that measure, billions of times the mass of our sun, and they belch out tremendous amounts of radiations, right? All kinds of radiation. So there's those kind of things, but I don't think there's any barrier per se, right?
Okay. Chuck, no barriers?
Not in my life. I'm barrier-free, quite frankly.
Thank you. Thank you very much. Yes.
All right, I have a fun question.
Good.
What emerging technology or scientific principle would you like to see explored in Star Trek Discovery when the new series comes out?
Oh, wow. What a great question.
Great question.
All right. Summer, you're thinking hard.
Thinking.
Okay, we'll give Andrew this first one.
I like medical stuff. I'm interested in that. That's such a hot topic today, is all the, let's see where we could go with what McCoy had, right? And the tricorder and stuff. And we're living in a time where we have wrist-worn medical devices, right? And there's this promise of being, non-intrusive medical tests. I've heard now there's a work on even doing like a glucose monitoring without any,
wow,
any puncturing.
No pinprick.
Save a lot of diabetics, a lot of suffering.
Go? I mean, I want to see that.
That's great.
Yeah.
Chuck?
I kind of like the medical thing too. I mean, when you think about it, even it's all in the news now, but when you think about the EpiPen and its delivery system, the first time we saw that was in the hypo with Bones, where he would just make that psst. And I was like, as a kid, I felt like, man, if only it were that easy. Just to get a needle like that would be awesome. So, yeah, it's a pretty cool thing.
I was thinking maybe like 3D printing. Because that's sort of something that's already like implied in that universe.
The replicator.
But it sort of just like magically happens. But I think that we're getting towards some of that, the very edge of the beginning of that. And even there's a 3D printer on the space station.
That's what I was going to say, yeah.
And so the astronauts can print a tool if they need it. Or if something breaks. It's kind of amazing.
Maybe one day they'll be able to walk up and go, tea, Earl Grey, hot. And
oh, wait. Thank you very much. Thank you. Yes.
I have two questions about gravitons.
Gravitons, ooh. You're not talking about that old 1970s Marvel super villain, right? Graviton?
No.
Not that guy. Okay. All right.
As far as I understand it, gravity should have a particle.
Yes.
And two things. When we find it, for the artificial gravity on the ship, could they be manipulating gravitons to keep them down? And second, if we do find it, could we maybe make a warp field sort of based on gravitons, so we don't need...
So instead of mass, you would manipulate the gravitons to create that bubble you were talking about.
I'll just put a little bit of a particle physics background on that question, and then I would love for Summer to give this a shot. I get the easy part, obviously. So, according to the current model of particle physics, there are 4 kinds of what are called bosons. These are the things that carry force. They mediate between the 4 forces of the universe. The strong nuclear force has something called a gluon. The electromagnetic force has something called a photon. And the weak nuclear force has something called the intermediate vector bosons, the W and Z particles is what they are. And for gravity, there thus should be a thing, another particle, because it's a force too, and it's called the graviton. But the graviton has never been detected, even though the other 3 kinds of particles have all been detected, and even though we know that gravity works, so there ought to be a graviton, gravitons have never been found. And so this is the point where we can now speculate from real science into science fiction.
But that's what Star Trek is basing. I think it's interesting that they've taken something like that's in the realm of theory and they've moved it forward. Is it possible to move forward from here? We don't know, but they have applied it in this wonderful adventure.
It's really nice. So, Summer, gravitons for artificial gravity or for warp drive? What do you think?
I don't know.
Okay.
But it's like, I mean, we knew that the Higgs boson existed, or in theory, we theorized that it existed, and we had to build massive, massive machines to attempt to just find a hint of it. So maybe we'll just continue to do that, and hopefully we'll have another international collaboration that will come together to find evidence of the graviton.
Wonderful.
Thank you very much.
Thank you very much. Yes.
You know, I love Star Trek my whole life. But one thing about it just hit me a couple weeks ago. And it actually happened when I wasn't watching Star Trek at all. I was actually watching Man of Steel. You ever see Man of Steel when Superman arrives on the Kryptonian ship that belongs to Zod and he's gagging and choking, he's not used to the atmosphere and all that stuff?
Tell me more.
It got me, it got me thinking, all right, every crew in Star Trek goes on to all these different planets. They can't all have the same type of oxygen and atmosphere and things like that for humans to breathe.
So really, I think the better question is, can you classify how they determine planets, like Earth being a class M planet and the other planets being different classes? Because that's really what he's talking about. Right. Because clearly, they're only beaming down to class M planets. So how is that determination made?
Yeah, well, I think you're right. Like in the Star Trek lore, there are those classifications of the ones that have the breathable atmosphere. And so in theory, I think to some extent, it's very possible that there are millions of planets in habitable zones because there's 100 billion stars in the Milky Way galaxy.
It's true.
And if in theory we're finding, potentially statistically says every planet could have a star, every star could have a planet. So out of 100 billion, you could easily have a million. And that doesn't even exhaust the ones that they've been to in all of the...
You could easily have 100 million out of 100
yeah,
billion.
Exactly.
Yeah.
And the elements, too, that we're talking about. Like we're discovering water is ubiquitous throughout the universe. We're finding them in nebulas. We're finding them all over the place in very unusual places, very distant, even other galaxies.
So I guess the answer is, although it is impossible that every planet has such breathable atmosphere, it is possible that there are enough breathable atmosphere planets that we actually can just fill 17 seasons of different Star Trek episodes. That's a great question.
Exactly.
Thank you.
That just make the whole thing just make so much more sense. Thank you, guys.
You're welcome. Well, this has been such a wonderful opportunity here to talk with you all, to geek out just a little tiny bit, but also bring some science down to earth into our kitchens, into our homes, here into New York. I think it's fair to say that this is the very, very best Star Trek missions panel that I have ever moderated and hosted. So I want to thank you all very, very much. Chuck Nice, my co-host, thank you so much for being here.
It's a pleasure. You guys are amazing. Thank you, each and every one of you, for coming out and spending time with us.
Andrew Fazekas, author of the book Star Trek, The Official Guide to the Universe. Thank you so, so much for being part of this wonderful thing, coming down from Canada for this. Summer Ash, my friend, thank you so much. Really appreciate everything that you're being here. Looking forward to hearing you on StarTalk All-Stars. And this is the book StarTalk with Neil deGrasse Tyson, which is available. This is StarTalk All-Stars, a live episode. Thank you all for being part of it. I'm Charles Liu. Enjoy the universe, everyone. Thank you so much.